Urmi Shah from IT/ICT Department of LG Institute of Engineering and Technology. Today we will be discussing with the second chapter of Analog and Digital Communication System, that is noise. In the previous sessions we have already discussed the properties of noise, what is basically noise, what are the sources from where noise is generated, from where noise is entering into the communication channel, what are the types of noises, how the classification of noise is done, and what is its formulation that we have seen in previous session. In today's session, we will be looking upon the derivation or the exact formulation for calculating the noise and the parameters related to it, and we will be seeing few more examples which will be based on the theoretical analysis of noise. So let's start with this session. So the topics which we are going to cover in this session are noise factor calculation for cascaded connection. Then we are going to derive the Friis formula, which is a generalized formula for noise. Then the third topic which we are going to discuss is noise temperature, and we will be seeing few more examples related to these topics. So this is the content of this session which we are going to see in this session. So let's start with these topics. So the first topic is noise factor calculation of amplifiers when they are connected in cascaded form. Basically, what is cascaded form? One after the another, the amplifier blocks are connected back to back. For example, you can see here in this diagram, amplifier 1 is connected with amplifier 2. Same way, more amplifiers can be further connected if this cascaded connection form is used. So here we are considering two amplifiers in cascaded form, and this amplifier are having their specific noise. The available noise at the output end of first amplifier is F1G1KT0BN. F is the noise factor for first amplifier, G is the power gain of first amplifier, and KT0BN is the associated noise power of any amplifier or any communication channel. Same way, this output noise power of first amplifier is available as an input noise power to amplifier 2 circuit. So I hope this arrangement is clear to all of you. Now whenever we will be calculating the output side power of amplifier 2, at that time the output power of amplifier 1 and the output power of amplifier 2 will be mixed up as an overall power of this cascaded form connection. So the overall power after the amplification at stage 2 or at the end of amplifier 2 is having the parameters of amplifier 1 as well as amplifier 2. So this is the output noise power for amplifier 2. The final equation which we are seeing in this slide, that is equation 1, is related to the output noise power of amplifier 2. Now you all might be wondering that how this derivation is done. Basically, at amplifier 2, the available output noise power of first amplifier was F1 G1 KT0BN. With it, the noise power of second amplifier we have added, that is F2 minus 1 KT0BN. That is the noise associated with amplifier 2 at its input. Hence, the total available noise power at the input of amplifier 2 is PNI2 F1G1 KT0BN plus F2 minus 1 kT0 Vn. So same way, this noise input power at the side of amplifier 2 is going to result in the final noise at the end of receiver of second amplifier, that is output noise power of second amplifier is PnO2 is equal to G2 into PNI2. PNI2 is the input noise power of second amplifier. G2 is the power gain of second amplifier. So that will be substituted here as in value which we have derived in the above section for PNI2. So the final equation for PnO2 will be G2 into F1 G1 KT0 Vn plus F2 minus 1 into KT0 Vn. So this is the derivation of power whenever we are connecting amplifiers back to back. So equation 1 is the freeze formula, or we can say the overall noise formula for amplifiers connected in cascaded form whenever we want to calculate the overall noise of any communication system. This way we can use the freeze formula for that cascaded system. So this is the freeze formula for the system which we discussed in this session. So next we will be looking upon is the final formation of freeze formula, or the generalized form of freeze formula which you can apply for any communication system having number of amplifiers. The system which we have discussed here is having only 2 amplifiers. But if you have more number of amplifiers and if you have lesser number of amplifiers, then we require some generalized formula also. So this is the generalized formula, which is freeze formula, which you can use to calculate the overall noise factor or overall noise power. So the overall available power of 2 amplifiers in cascaded form is having 2 power gains G1 and G2. Both amplifiers are having their own power gains and the overall noise factor is capital F. So the output noise power is having PNO is equal to F into G into KT0Vn, where G will be equal to G1 into G2. It will be product of the gain of both the amplifiers. So equating equation 1, which we have seen in previous slide and which we have seen in this slide, when we will compare equation 1 and 2, we will be able to keep the value of PNO as F into G into KT0Vn. So instead of PNO2, we are equating this equation 1 with FG So this is the generalized formula after nullifying all the factors. If you have 2 amplifiers in your cascaded form connection communication channel, then the generalized formula, freeze formula, is Fg is equal to F1G1 plus F2 minus 1. So this is the freeze formula for communication channel. We will see more examples related to this in the upcoming sessions. Freeze formula which we have derived, we are dividing it by the gain so that we will get overall noise factor. So F we have derived here is equal to F1 plus F2 minus 1 upon G1. This is the final formulation for freeze formula if you are having only 2 amplifiers in your channel. If you have 3 amplifiers again, you have to subtract the noise factor by 1, F3 minus 1 upon the gains of your previous amplifier, that is G1 and G2. So basically, if you have 3 amplifiers, at first amplifier you will have the noise factor, that is F1. At second amplifier you will have F2 minus 1, that is the noise factor of second amplifier, divided by the gain of previous amplifier, that is G1. If you have third amplifier, then at that stage you will have its own noise factor, that is F3 minus 1, Then you will divide it by the gain of previous two amplifiers. So this is the generalized Friis formula. Next, we will be seeing is the topic noise temperature. The concept of noise temperature is available from the noise power equations only. Here we have equation Pn is equal to KTAVN. Here Ta is the available temperature of the atmosphere, or we can say that here Ta indicates the noise temperature associated with available power. So whenever we are using this noise temperature concept in our amplifier diagram or in our amplifier based communication system, it relates the equivalent noise of amplifier, which is referred as input side. If the amplifier noise is referred as an input, which is denoted by PNA, that is the noise generated by amplifier, noise power generated by amplifier is PNA. So the equivalent noise temperature will be TE is the equivalent noise temperature. Equation 3 represents the formulation for equivalent temperature. So T is equal to PNA divided by KBN, which is coming from the equation which we have discussed in top. So this is the equation for noise temperature, which is the equivalent temperature associated whenever an amplifier is having some input noise. So this is the formulation of noise temperature. Next we have seen is the formulation of noise temperature in form of Friis formula. Friis formula can be expressed in terms of equivalent noise temperature by denoting TE. TE is your equivalent temperature in terms of overall noise of cascaded system having temperatures T1, T2, T3 up to so on, depends on the number of amplifiers. So the Friis formula, which is derived based on the Friis formula, is T is equal to T1 plus T2 divided by G1 plus T3 divided by G1 G2, which is exactly replaced by the noise factor formula which we have derived for Friis formula in terms of F. In place of F, we are replacing it with the equivalent temperature. So this formulation is the overall temperature of any amplifier circuit which is arranged in form of cascaded form. This is the formulation for equivalent temperature. Let's see some examples related to the derivations which we have discussed in this session. So the example asked over here is a mixture stage has noise figure 20 dB. Now noise factor whenever expressed in form of log or decibel, we call it as noise figure. So we need to calculate noise factor from noise figure by taking the anti-log of 20 dB. So that is 100, which we have calculated here in terms of F2. F2 is 20 dB, so it is equal to 100. And this is preceded by an amplifier which is having noise figure 9 dB. So first amplifier is having 9 dB figure as noise, and the second amplifier is having noise figure 20 dB. So F1 for first will be anti-log of 9 dB, which is 7.94. You can calculate the anti-log of the noise figure so that you can have the noise factor. So F1 is 7.94, F2 is 100, G1 and G2 are already given over here. So in this question, the available power gain is 15 dB. The overall power gain is 15 dB. So that you need to again convert by taking its anti-log. So it will be 31.62. You just have to assume all this value in the Friis formula. So you will get the overall noise factor. Noise factor, once you have achieved, you need to convert it in form of 10 log of F. So you will get noise figure. So this is the formulation which we have discussed in today's session, and based on that we can have these examples These examples can be asked in your GTU exams. So you can refer this kind of exam based on the formula which we have seen today. Another kind of example which can be asked in your exam is this, based on equivalent noise temperature. Here, a receiver is having a noise figure of 12 dB and it is fed by a low noise amplifier having gain 50 dB. So the noise temperature here is 90 Kelvin. We are calculating the equivalent noise temperature. So using this data, you can simply put the values in the equation and the overall noise temperature here is 90 K. So this way, you can solve the examples related to the formula which we have discussed in today's session. I hope these examples are clear to you and the formulations which we have discussed are pretty much clear to you. You can refer following books for this session. Thank you for watching this session. In the upcoming session, we will be starting with another chapter of this course, Analog and Digital Communication, which will be related to modulation techniques, and one of the finest modulation technique is amplitude modulation that we will be discussing in the next session. Thank you so much for watching this session. Thank you.